Hi guys, this video is going to talk about why we use Lewis structures. Just from the previous video, it's kind of clear now to you, hopefully, that Lewis structures, although it's fairly easy to draw, it doesn't represent some of the properties of molecules. That's why we have those exceptions to the Lewis rules, the octet rule, for molecules that have fewer or more than 8 electrons around their valence shell. It turns out that the Lewis model can't really explain the behavior of those types of molecules or the odd electron molecules, right? However, they're still widely used, and the reason is the following. There's a couple of reasons. The first one is the one that we're going to talk about in this video. It turns out that you can use Lewis structure, which is just this drawing of atoms with some dots around it for electrons that really doesn't represent reality. You can actually use it to predict what the molecule will look like in 3 dimensions, and that's a very powerful technique which we will discuss later on in this video. And the next video will then talk about how you can use these structures that you predict to then help you figure out the polarity of the molecule, yet another useful property of a molecule. Okay. The second component of why Lewis structure is still being used is that in organic chemistry, because the components of organic molecules are all second period elements, as listed here, all carbon, hydrogen, nitrogen, oxygen, and halogens. These are atoms that actually obey the octet rule. So in other words, the Lewis structure can be used fairly confidently in this case to represent these molecules. And it turns out that in organic chemistry, it's very useful to draw these Lewis drawings because you can then represent how reactants become products. And you will learn a lot more of this when you take organic chemistry. So the topic that we will get into now is the idea of three-dimensional molecular structure. Okay. Now, what exactly is the difference between the Lewis structure and the molecular structure? Well, a Lewis structure is basically a two-dimensional structure. So it's shown right here as an example with some basic geometrical shape like a rectangle, triangle, and a circle. These are all two-dimensional objects, right? So in other words, when you look at them, you just see their length and width, but you don't get a sense of how deep these structures are. However, these are basically, you can convert them to a three-dimensional object. For example, the rectangle might actually be a cube of some sort that looks like this. Okay, now you get a feel for the depth of the object itself, and the circle might actually be part of a cylinder where you're looking at it top down, and then you get a feel for, again, the volume of these objects. Okay, and of course molecules are also a three-dimensional object. We live in a three-dimensional universe, so in order to be able to understand what a molecule looks like and how it does some of the functions, you really need to understand what it looks like in 3 dimensions. It's not really enough to have a two-dimensional representation of the molecule. And that's really what we want to talk about in this video, is how you can convert the Lewis structure, which is again your two-dimensional model, into a three-dimensional visualization of the molecules. Here, for example, is a three-dimensional look of a molecule that you can also draw as a Lewis structure in a two-dimensional mode. But you can clearly see, once you have it in 3 dimensions, you see a lot of the features that you can't really see in a two-dimensional model. You see how the molecule bends. You have a little kink here. You have a little groove here for the molecules. And you have all these different pockets that around here might be a little hard to see if you're in 2 dimensions. Okay? And all of these parts of the molecule are very useful to understand, because it turns out that when you have molecules like this, when they interact with other molecules, this is where the other molecules are going to come in. So they perform binding interaction maybe on this side. Maybe another molecule will come in and bind on this side. So a lot of these properties are very useful and can only be understood in a three-dimensional context. So the question then is, how do we perform this operation? We want to take Lewis structures, which are two-dimensional structures, and we want to convert them to three-dimensional molecular shapes or molecular structure. What you need to understand in order to be able to do this is a theory called VSEPR. Okay? What does it stand for? It stands for valence shell electron pair repulsion theory. Okay? Now, it might be a mouthful and you might think, well, this seems kind of difficult to understand, but really the idea is very simple, as I would illustrate in the next slide. So the idea of the VSEPR, or usually we call it VSEPR model, is the following. In any Lewis structure, you usually have a number of bonding pairs and lone pairs, right, drawn around it. So for example, you can imagine that you have an atom here, A, and then you have maybe a bonding pair here, a bonding pair here, and maybe a lone pair right here, okay? And what happens here is, for example, let's say it's bonded to two of these B atoms, okay? So what happens here is just that the theory proposes, because these electrons are all negatively charged, okay, they're going to repel each other. So in other words, there's repulsion here, there's repulsion here, and there's repulsion here, okay, between all of these pairs of electrons. Because these pairs repel each other, they want to be as far away from each other as possible, okay? As a result of wanting to be as far away as these electron pairs then forces the molecule to have certain shapes, okay? So that's the idea there. As a result of the repulsion, you automatically assume certain geometric shapes that you can predict ahead of time just by using math, okay? And these are the following geometric shapes that you will get also. If you were to have, for example, an atom that looks like this, where you have two pairs of electrons around it, so A is your central atom, and then you have two pairs of electrons, whether it's bonding or lone pairs, automatically the best structure you're going to get in order to be able to put those two pairs of electrons as far away from each other as possible will be a linear shape, okay? So that can be shown a lot of times with a demonstration with two balloons that are connected together. Automatically, if you have two balloons, they're going to spread out in a linear shape. So in other words, the angle between these two atoms here, right, the XAX angle as shown by this particular picture, will be 180 degrees, okay? So that's if you have two pairs of electrons around the central atom, automatically your electron pair geometry, which is shown right here, is going to be linear, okay? If you have three pairs around the central atom, then automatically the structure that you would get would look something like this, as shown by the balloon, or as shown by your picture right here will be a central atom in the middle and then three atoms around it, or three pairs of electrons around it. This is what we refer to as a trigonal planar. Now here I noticed that it says triangular planar, but usually the more common phrase to use here is trigonal planar. And you can go on with the other shapes as well. So if you have four pairs of electrons around the central atom, it's going to be called a tetrahedral shape. If you have five pairs, it's going to have this shape, which is referred to as, I'm going to write it here, trigonal bipyramidal. And then lastly we have octahedral, which is six pairs of electrons around the central atom, and again that would be called octahedral. Okay, so I hope here when I'm presenting the picture of these geometric shapes right next to the atom pictures, right, I hope that it would make it a little bit clearer why they're called certain names. Now the linear shape, which is the first one, and then the trigonal planar shape, tetrahedral shape, those are fairly self-explanatory, I hope. And then the one that's usually an issue, a little hard to understand, is the trigonal bipyramidal. So if you look at this shape here, which is trigonal bipyramidal, what you see is that basically you have a base, a triangular base, right, which is formed by these three atoms in the middle. So 1, 2, 3, that's your triangle that forms that base, okay? And then if you connect each of the middle atom with the top atom, you get a pyramid, okay? So that's your first pyramid, okay? And then if you connect each of the middle atom with the bottom atom, then you get your second pyramid. And that's why they're called trigonal for the base and bipyramidal for the two pyramids that are formed. Octahedral is basically the same, as you can see right here. Octahedral is the same like trigonal bipyramidal, except that the base is a square, okay? So then what you have is you have a point at the top connecting to all these points in the middle, and that's one pyramid, and then the other pyramid would be at the bottom right here where it connects to all of these guys, okay? So it's basically two pyramids with a square base. That's what octahedral is. Just to close off this video, I want to mention that the shapes that we just learned are what we call the electronic geometries of this particular structure. In the next video, we would then talk about what the molecular shape will be for each of these electronic geometries. and for that you would have to take into account the bonding and the lone pair.